All right, everybody, let's move on to our next analysis of variance that we need to learn, which is called the factorial ANOVA. Let's just jump right into the what and the when. So the factorial ANOVA is the one that uses at least two or more independent variables. So it's looking at least two, but it could look at three or four. And it's looking at the effect of each independent variable the effect of each independent variable on the dependent variable, but can also look at how the independent variables combine to affect the dependent variable. So you would use this when you have at least two or more independent variables. That's a dead giveaway. And remember that each independent variable has to have at least one level. Typically it'll have two, but it's possible that it could just have one. It could just be one variable that measures just one thing. Okay. Now with the ANOVA, the IVs are always categorical and the DV is always continuous. Now, something that's specific to the factorial ANOVA that you need to learn is something called the factorial design or the experimental design. Essentially, it's a conceptual layout. Think of it as like kind of the blueprint for the factorial ANOVA. It symbolically and visually shows what's going on with the ANOVA. So the way that this is represented is using the notation you can see there below, which is a number times another number. No spacing in between these symbols here. So the number of numbers that you see, so like the number of pound signs, those are placeholders. So normally would actually be a number of some sort, like 2 times 2, but I'm just using this as, kind of an example with placeholders. So the number of numbers that you see is how many independent variables you have in the analysis. So if you see 2 numbers, that's 2 IVs. Now the number itself tells you how many levels of each independent variable, how many levels that independent variable has. So let's do an example. So let's say that we have the scenario if we want to look at seasonal time of year and parent gender. Well, I have 2 independent variables. So that's indicated by 2 numbers there. And the number itself tells me how many groups or how many levels of the independent variable. So seasonal time of year has 4, so we use the number 4 to represent that, and parent gender has 2, so we use that to represent that. So we have a 4x2 factorial design, meaning we have 2 independent variables. The first one has 4 levels, the second one has 2 levels. Now the factorial design can also be represented using a table, much like the one you've seen here. You saw this last time in the one-way ANOVA slides. So we have the columns being the first one and the parent gender being the second one. Again, it is a 4x2 factorial design. Now, let's talk a little bit about the logic of the factorial ANOVA. So remember I said that in the factorial ANOVA, it can look at the individual effects of each independent variable on the dependent variable. When you're looking at the individual effects of the IVs, this is called the main effects. You're looking for the main effect of just one independent variable. So this is an example of what a question could be looking at for a main effect. Is there a significant difference between the average effects of the seasons on hours spent with children? That would be, is there a main effect? Is there a main effect for independent variable 1? Is there a significant difference between the average effects of parent gender on hours spent with children? Is there a main effect for the second independent variable? Now, the thing that most people use factorial ANOVA for is when they want to look at the combined effects of the independent variables on the dependent variable. They want to know, do these 2 things interact with each other to affect the DV? So, for example, is there a significant difference between the combined average effects of seasonal time of year and parent gender on hours spent with children? So is there an interaction between IV1 and IV2? Now, the examples of the questions you're seeing here, these are good templates to use when trying to craft your research question for the specific problem that you'll come across. Especially for the interaction here, you can use this wording you see on this slide as a template for how to write your research question. Now, you're looking at the combined effect. So what are you looking at there? Well, you want to see the average amount of time, so you have the mean of each combination of the variables, and then you also have the totals. So what is the average time fathers are spending with their kids regardless of seasonal time of year? You got the mean of father. Do the same thing for mean of mother. We can look at the average time in each season regardless of parent gender. But we can also look at the combination. So what is the average amount of time fathers are spending in each season, and the average amount of time mothers are spending in each season? Now, if I only wanted to look at the effect of season, I would just look at the means that you see here at the bottom. I don't want to see if there's a difference between those means. That would be the main effect of independent variable 1. If I want to look at the difference between just the means of parent gender, that would be looking for the main effect of just the second IV. And then if I look at all these combinations, that's where I'm really interested in the interaction of the independent variables here. So a factorial ANOVA can do all of this all in one analysis. It can look at the main effects and it can look at the interaction. So let's get into specifically how we can calculate a factorial ANOVA. So let's start with this general question to phrase our context. Does college major and gender interact to affect class attendance? So does the major that you have and the gender that you are interact to affect how much you go to class? So we can take that general question and we can phrase it into the more specific research question. Notice that the wording of the research question here is following the same format as the one that I showed you a few slides ago, using that template there. So is there a significant difference between the combined average effects of college major and gender on class attendance? So here are some characteristics that indicate the factorial is what you want to use. One, you're looking for mean differences. We see the key words there, difference and average. You have at least two IVs. You see college major and gender, two different independent variables being mentioned there, okay? And then you see the interaction of the two or more IVs on one DV, right? The dependent variables class attendance, you see that keyword combined average effects, right? Is it combined indicating interaction? That's the question. That's indicating you got to use the factorial ANOVA. Now, how are our variables set up? Well, not much different than how you've seen them before. You've just got another independent variable to account for. So we have independent variable 1, which is college major. It's the first one mentioned. All right, the first variable could be gender, but the first one that's mentioned in the research question is just by default independent variable 1. So it's categorical, and we have our three categories here of psych, soc, and biology majors. Second independent variable is gender. It's categorical because we have male and female. And then our dependent variable is class attendance. It is continuous, and it falls on a scale of 0 to 6. Okay, let's say that I measured them over a 2-week period, and they could have attended class 3 times a week for 2 weeks, so a total of 6 class periods. So I want to know, is there a difference between the average attendance over 2 weeks by looking at the combination of a student's major and their gender, and if it affects the average amount they attend class? So remember, the factorial design that we have here is should be a 3x2. First variable has 3 groups, second variable has 2 groups. So it is a 3x2 factorial design. So let's continue on with how we can calculate this. Okay. So there's a few things that we have to take note of. Okay. First, we have to notice what our first independent variable is. We can just call it variable A for the sake of succinctness. So that's college major. Independent variable 2 is variable B, that's gender. And AV is the interaction of independent variable 1 and 2. Now, lowercase a tells us the levels of variable A. We see that there's 3 college majors, so the levels are 3. B, lowercase b, is the number of levels for gender. There's 2. Little n is the number of people in each cell, and big N is the total amount of people in the study. Okay, or sorry, the total amount of yes, total amount of people in each cell, and then the total amount of people that we have. Yes, just like it does for the one-way ANOVA. Yeah, little n is the amount in each group, and n is the total overall. So we have 18 students overall that we looked at, and we see that we have 3 in each combination. 3 male psych, soc, and bio, 3 female psych, soc, and bio. And as you can see here, I calculated the means for us ahead of time just so we could jump right into the calculations here. So we see that psych and male go on average of 3, soc 3.7, and so on. You can read the rest of the numbers. Look at the totals here. The average time males are going to class is roughly 2 days out of 2 weeks, and females are about 1.7 days, almost 2. You can see for majors, social majors are going about 3 days out of the 2 weeks, Psych 2, Bio 1, and the grand mean overall is across all 18 students, the average attendance is about 2 days over the course of 2 weeks. Not going to class very often, these students here that we see in this data set. So what we need to do is calculate the between group variance and the within group variance, and we need to do that for each independent variable and the interaction. So the factorial ANOVA, just by necessity, is going to be longer because we have more variables that we need to work with. So we need to calculate the same things we did with the one-way ANOVA. We need to find sum of squares, then mean squares, then we find our f-scores. But we need to do this for each variable and for each interaction. So because we have 2 independent variables, we need to find sum of squares for A, sum of squares for B, and then sum of squares for the interaction. That would be sum of squares AB. That's calculated by using something called SS cells, which is essentially looking at the difference between the means of each cell that we saw on the table there. And then SS within is calculated across all the combinations, all the groups, and again, it always represents sampling error. So SSA represents how much the cell means differ due to the first independent variable. SSB is how much they differ due to the second independent variable. And the interaction, SSAB, is how much they differ due to the combination of A and B. So went ahead and already calculated these for you. The equations for them are complicated and you don't really need to get bogged down with that. The software is going to calculate it for you anyway. I want you to focus more on the clearer calculations so you can actually see what's going on here. So we have our SSA, SS for B, and SS for the interaction, okay? Which is 8.83, and we have our SS within sampling error 6.59. Now we can find our degrees of freedom, which I have for us here. You take for the degrees of freedom for A, for the first variable, this essentially would be, all these are going to be degrees of freedom betweens, the between for each variable and each interaction. DF within is just DF within for across the whole analysis. So DFA, or DF between for A, is the number of levels A has minus 1. That comes out to 2. DFB is the number of levels, 2 minus 1, which comes out to 1. Degrees of freedom for between for the interaction is degrees of freedom A times degrees of freedom B. So 2 times 1 is 2. And the degrees of freedom within comes out to be 12. As we have here recorded in that table at the top. So now that we have our sum of squares and we have our degrees of freedom, now we can calculate our mean squares. And the mean squares is represented the same thing it did in the one sample t-test. We just have multiple of them, right? Mean squares A represents the variance between the groups of the first independent variable. MSB, same thing for the second independent variable. MSAB is for the interaction. And then MS within represents sampling error. So you can pause the video at this point and do these simple calculations and calculate the mean squares, all the 4 ones that we need. All right, so these are the numbers that you should have gotten, okay? And I put them in the table there. Double check to make sure that you got the right, that you came to the right conclusion. So we have for variable A, 7.08, 1.36 for B, 4.42 for the interaction, and a sampling error of 0.54. That's pretty encouraging. Got a smaller sampling error. That's definitely closer to 0. So what is our f-score going to represent? Well, as we already determined in the one-way ANOVA, the top is the difference between the group means, the bottom is the sampling error, okay? We have to find that for each variable. So we have to have an f-score, which represents the difference between the group means, while also factoring in sampling error, for each independent variable and for the interaction. So if you have 2 IVs, you have 2 IVs and that means 1 interaction. So you're going to have 3 f-scores that you have to calculate in that scenario. You keep adding independent variables on, you're going to get more and more f-scores you have to calculate. So go ahead and pause the video and do these calculations here and find your 3 f-scores. Now this is what you should have found. The f-score for college major is 13.11. The f-score for gender is 2.51. For the interaction is 8.18. So what is this number representing? Okay? The F-score is a ratio between group variance to within group variance. It's the difference between your means, factoring in sampling error. So a bigger F-score for the variables and for the interaction, bigger F-score indicates bigger differences between the group means. The F-score means the exact same thing, and the ANOVA and this one-way ANOVA and the factorial ANOVA and F-score means the same thing. A bigger F-score, bigger differences. But a larger sampling error, a larger MS within, results in a smaller F-score. Now, our MS within is actually pretty small, so that's encouraging. So we know that our F-score is representing more so the differences between our group means for each variable and for that interaction. So that's how you calculate the factorial ANOVA. It's a little lengthy, right? Thank goodness we have technology that can do it for us, because doing it by hand is quite tedious, I can tell you from experience. But the software does it for us. Now, in our next video, we're going to look at the factorial ANOVA in the context of hypothesis testing.